All right, grade 12 chemistry, SCH4U. This is your first video. This one is called Quantum Mechanics for Chemists, or alternatively you can call it the quantum model of the atom. Our goal really is to be able to understand these kinds of diagrams. These are called Aufbau diagrams. This is iron. We're going to get to that later. I know this note says tomorrow, but it's going to be next week. But the important thing here is to help you understand where this model comes from, the theoretical evidence underpinning our quantum model of the atom. In terms of what the curriculum says about this, is you have to understand terms like emission spectrum and energy level and photon. Those are all going to come up today. And to talk about how Bohr and Rutherford contributed to the planetary model of the hydrogen atom. Bohr in particular used spectroscopy a lot, this idea of emission spectrums and energy levels in order to create his model. We're also going to learn about these guys, Balmer, Rydberg, Planck, Einstein, DeBroglie and Schroedinger. Those guys are not going to be on any tests or anything like that, but they're very important in order to understand, this stuff, basically. I'm not going to talk about these right now. That's going to be, next week. But this stuff is an underpinning. It's a background in order to get there. So let's talk about what we're actually going to talk about today. Here are our learning goals. First off, a theoretical background of spectroscopy. What is spectroscopy? Why is it useful? When was it invented? That kind of thing. Then the early attempts to model the spectral lines that we got from spectroscopy. Then we get into the good stuff, Max Planck and Albert Einstein. And then Rutherford and Bohr, the actual curriculum stuff. That's something that you need to know according to the curriculum. And then the last piece is DeBroglie and Schroedinger. You might have heard of Schrodinger's cat. We're going to talk a little bit about Schrodinger's cat. So we're going to take away this. Just a little quote from Wikipedia here. Quantum mechanics cannot easily be reconciled with everyday language and observation. Its interpretation has often seemed counterintuitive to physicists, including its inventors. You might have heard some fancy stuff about quantum physics, particles being in two places at once, things teleporting through walls, lots of stuff about probability. Some people say that quantum mechanics is the reason that we have consciousness and souls and things like that. I'm not going to get into any of that stuff. I'm just going to give you the theoretical background and the experiments that led to the development of the quantum theory of the atom. Let's just jump right in. Our first thing is a theoretical background of spectroscopy. What the heck is spectroscopy? This is how spectroscopy works. I'm sure you've all seen light go through a prism or a door or something like that and makes a rainbow on the wall. Turns out that works with very hot objects and you get this continuous spectrum. But if it's one specific element, you end up with lines. You end up with emission lines instead of just a continuous spectrum when you spread it out. If you take the continuous spectrum and run it through a cold gas, you get an absorption line spectrum instead. And those absorption lines are in the same place that the emission lines are. So hey, there's something there that's specific to each element. I actually did a quick little example of this, and I did it with just a CD and my light bulb. You see my light bulb there and the CD reflecting it. We're not really interested in the reflection of the light bulb in the CD. What we're interested in is this little rainbow guy on the side, right? So the CD, because it's got little grooves in it, is acting like the prism. It's actually a diffraction grating that it's acting like. And we're looking at it through the diffraction grating. And you see that little rainbow fringe. But if I do something a little bit fancier and I turn the light bulb sideways and look at it through the CD, you get a better look at the spread of the spectrum. You see there's some red, some green, and some blue. A noticeable lack of yellow, right? And then you can get a little bit even more clever and actually just nick the top of the light bulb, just the top of the light bulb, and those lines become much more visible. So those are emission lines. Those are emission lines from the hot ionized gas inside this CFL light bulb. One of those gases in there is mercury, and you can actually see that on this diagram. You guys see that there's this red, there's that red for mercury, that really bright green, that's a really bright green for mercury, and this blue is the mercury blue, and this blue is also kind of there too. So you can actually tell that there's mercury in this light bulb just by looking at its reflection in a CD, at its spectrum, at its emission spectrum, which is one of the words that we need to know. So an emission spectrum is what happens when you run, when you look at a hot gas through some kind of prism or diffraction grating, and you see those spectral lines. This was discovered in the early 1800s, maybe like even maybe late 1700s. So it's been around for a long time, but being able to interpret it and link it to specific elements took quite a bit longer than that. So I'll take away that picture. Oh, never mind. So there's my picture with the light bulb. So that's the same light bulb, right? The same light bulb and the emission spectrum lines. Feel free to do this at home with a CD or a DVD. You can do this with all kinds of things, with different light sources. Try your phone's LED thing. That works pretty well. Or maybe your TV, the LEDs on your TV, stuff like that. I also did this with my aquarium. So I tried the same thing with my aquarium. There's the CD and there's my aquarium light. And if I zoomed in on it, there's a spectrum of my aquarium light. But you might notice that it's different than those lines, right? There's, for example, a bigger green spectrum. There's a bigger, brighter green. There's an orange that doesn't really exist on that spectrum. And there's a deeper red, a deeper red, and a much deeper blue, almost purple up in the corner that doesn't really happen here. There's no like big purple thing. So it tells you that there's different elements in my aquarium light than there is in my CFL, in my spiral light. So we'll take that away. And so that's spectroscopy. It's the basics for quantum mechanics. One neat thing about spectroscopy is here's a spectrum of the sun. The sun. This was made by Fraunhofer, who was a German in 1815 or something like that, 1814. And he saw these dark bands in the solar spectrum and very carefully cataloged like 500 of them, 500 different bands in the sun. And he put letters to them for the really, really bright ones and where they should go. Later, when they looked at the Fraunhofer lines, they realized that, hey, look, there's hydrogen. Hydrogen matches some Fraunhofer lines. C, F, little f, and little h match up to hydrogen. Sodium, this bright sodium matches up to this bright sodium here. And then when they looked at it, they realized, hey, this B, right, that doesn't match any elements that we know. And some other ones were the same way. So this B and this little A didn't match elements that they already knew. So they're like, there must be a different element in the sun that we haven't seen on Earth yet. And it turns out it was helium. So helium, the element, was actually discovered on the sun before it was discovered on Earth using spectral lines, which is always a really cool fact. It's called helium because helios is the sun in Greek, helium literally means sun element because it was discovered on the sun. The only element that wasn't discovered on Earth, discovered on a star before it was discovered on Earth, which I think is really cool. All right, so that is a theoretical basis for spectroscopy. You should understand this idea that different elements make different lines when they get excited, when we shoot gas, when we shoot electricity or make them hot or whatever, when they get excited, they make different spectral lines. There's a kind of an applet for this, a PET applet. I'll have a link to that down below, and we can start shooting light at oh, come on. It doesn't want to shoot. Oh, here we go. Right. So we start shooting light at it of different wavelengths, lots of different wavelengths, and you see that sometimes a little wavelength comes out, and this is keeping track of what comes out. This is a hydrogen atom, and if we make it go fast, it'll start building up different things. Most of them are in the ultraviolet, most of them are in the UV, but every so often you might see one that pops up in the visible. And this is, this is what they did. They would shoot light of all colors. Oh, there's a red one there, right? They would shoot light of all colors. I'm going to let this go for a while I talk about other things. So, okay, so we were looking at theoretical background of spectroscopy. Next up, we're going to talk about early attempts to model these spectral lines, specifically the spectral lines of hydrogen, so the simplest element. It has relatively few lines, and they look like they make this cool pattern. If you guys look at this pattern, have a minute to look at that pattern and just kind of, what does it remind you of? Think physics, because these were physicists doing this. While you think about that, I'm going to pause and I'm going to fix the stuff around here. Okay, we're back off pause, and we're going to talk about early attempts to model spectral lines, specifically the hydrogen spectral line to start off with. So when we look at this, if you said it looks kind of like maybe a quadratic, maybe it looks like something getting further away and accelerating like in physics, that would be, you would be in the ballpark of what Mr. Balmer thought. Johann Balmer in 1885. Remember that they discovered these lines in the early 1800s. Even as early as 1815, they found 570 of them in the solar spectrum. But Balmer, more than 50 years later, he developed this formula to explain these visible lines in hydrogen. These ones here, those ones that look like a squared pattern. And if we go back over here, you can see them here. They get closer together as we get towards the ultraviolet. What Balmer came up with was this, that the wavelength lambda was some value b, so he called it the Balmer wavelength, 364.5 nanometers, to the power of n squared over n squared minus 4. Right, so that's the formula that he came up with for the hydrogen atom. The 364.5 was this red here. Was this UV? It was in the UV. 364 was in the UV, and then it would get further out on a square, on a squared relationship. So that's 1885. 3 years later, after Balmer made this, Johannes Rydberg, expanded it. He expanded it to include other series that people found out. So there's the Balmer series, there's this series down here, the Lyman series, other series here, the Fund, Passion, and Bracket series. And he said he made it work with other formulas. And one way that he was able to do it was turning this fraction upside down, because he was like, hey, it's easier to go divide by n squared than it is to divide by n squared minus m squared, because then you have to simplify your fraction and cross multiply and whatever. He's like, no, I'm just going to flip the fraction, it's easier. So he went 1 over wavelength when he was making his formula, and 1 over wavelength was something he called the wave number. The wave number, the inverse wavelength. So that's how many waves can fit in one space. It was accidental. It was an accidental kind of thing. It just made the math easier for him. But then it turns out that the amount of waves that can fit in a space is a really good way to describe how electrons actually exist in an atom. So yeah, it was accidental, and it accidentally created this concept of energy levels. But the formula itself wasn't thinking about that. The formula just wanted to explain why these lines are where they are, like how do we predict where these lines are going to be. Balmer was also, or sorry, Rydberg was also able to make it work for any other atom, where Z is the atomic mass, or that's the charge. Z is the charge of the atom, and R is Rydberg's constant, which is some specific number that he used, kind of like the Balmer wavelength was 364.5. Now, 1900, 100 years basically after they invented the science of spectroscopy, Max Planck, who's our next topic, discovered that the energy of light is proportional to its wavelength. If you know what the wavelength is, you know exactly what energy that light had. That was the next key to create this concept of energy levels, because here's your wavelength, so that wavelength is energy levels, or is related to energy levels, and so this also gave you an idea of energy levels, right? Took a little while, and then Niels Bohr used Max Planck's idea and Rydberg's idea together, and he kind of put them together and explained, hey, they're actual physical aspects, they're called energy levels. He proved it with experiment. That experiment was spectroscopy, was exactly, this kind of stuff. Well, not that exact kind of stuff, but a more, specific version of that with a lot of math behind it, a lot of statistics behind it. So math and statistics is going to be our next thing, because we're now going to talk about Max Planck and Albert Einstein, whose name I forgot the T in Albert Einstein. Let me fix that. Put that T there. So, Max Planck and Albert Einstein, what's their contribution here. I'm going to pause and fix this up, and I'll be back in a sec. Okay, so now we're going to talk about Max Planck and Albert Einstein. We just finished talking about how a lot of this came from spectroscopy. So here's the beginning of quantum mechanics, the very, very beginning of quantum mechanics. Once again, you're not responsible for any of this math. You'll see it in grade 12 physics, but we don't do anything with this math in chemistry, not in grade 12 chemistry anyway. So Planck and Einstein. So who's this Max Planck guy? He was working on this problem called the black body problem, where they were trying to find a curve that would fit what they saw when they had that spectrum from hot objects. That's called the black body spectrum. The hotter the object is, the more towards the blue this spectrum shifts, and the more radiation it releases in general. And they thought they had a good one that worked in the infrared, but that formula did not work when you got near visible light. In fact, it predicted that the maximum possible thing, that once you got into ultraviolet, you'd have to have infinite energy. But clearly the sun gives off ultraviolet light, and is just a hot object, and other things gave off ultraviolet light just being really hot. Clearly it wasn't infinite energy, because that just seems odd. So this law wasn't working. Rayleigh-Jean's law wasn't working. Planck came up with a law. But what Planck did was a lot the same thing as what Rydberg and Balmer did, right? They went to the math and they tried to model it with math without even thinking about what the physics means. They just went, I'm going to throw math at it. So that's what Planck did. He applied this new study called statistical mechanics to the results, and he forced the model onto the physics instead of trying to use physics to come up with the model. This was completely backwards from how physics was done up until those days. Up until those days, physicists would have this model in their head of what was going on, and then they would take what they knew about that model and try to math out what it would mean. So Rayleigh and Jeans were trying to explain this stuff kind of like oscillators, like weights on springs going back and forth, making electromagnetic waves. Planck kind of threw that out the window and went, what does this math tell me? And what the math told him was that the energy of light was discrete, that specific wavelength of light had to be carrying a specific energy, that light of a certain frequency could only have that energy. So how do you get more light in one energy than you do in another energy? You just need more oscillators. The oscillators aren't going bigger, there's just more of them, and they're all moving the same. That was what Planck's math told him was what happened. And he went, okay, well, I mean, it fits the data incredibly well, so I'm going to keep it as a formula that kind of helps us predict blackbody radiation. But he felt that concept of a bunch of radiators and that light has to have a specific energy, he thought that was a weakness in the theory. He thought it was a necessary assumption. He didn't think it meant anything bigger. Other people didn't either until 5 years later, this guy named Albert Einstein, for his thesis, his PhD thesis, I think. It's a paper that he put out while working on his PhD. Took Planck's equation and applied it to a completely different thing, which was called the photoelectric effect, which had to do with how light knocks electrons away from different metals. People had noticed that you could shine, no matter how bright of a red light, you shine whatever brightness of red light you wanted to on a metal, or a specific metal, the potassium for example here, and no electrons would leave. As much red light as you want, the brightest red light in the world, and no electrons would leave. But as soon as you even gave it a little bit of green or a little bit of blue, an electron would pop off. This doesn't make sense if you treat light like a wave, because brighter light would just be a bigger wave, so it should carry more energy. But it does make sense if you use Planck's idea of light quanta, where each individual oscillator has to have a specific energy. So red would never have enough energy to kick out an electron. This got a bunch of attention. Albert Einstein, he got a lot of attention for this. This was one of his 4 miracle year papers in 1905. And this was, in fact, why Einstein got a Nobel Prize. He got his Nobel Prize for this. People think it's for relativity, but he got it for explaining the photoelectric effect using Planck's statistics. So Einstein's treatment kind of said we can think of Einstein's treatment said that we can treat light as a particle, and it would explain what was going on. But Planck and Bohr as well, we haven't talked about Bohr yet, but Planck and Bohr both denounced this idea. They're like, no way, no, light can't be a particle. Planck said, no, that's just a mathematical trick I was using. I'm still working on trying to figure out where I went wrong, but for now it works really well. Einstein's like, no, it's a particle, guys. We can treat it as a particle in this specific case. Of course, eventually he was proven right. Almost 20 years later, he was proven right in that light was a particle. It's now called a photon. And after he was proven right, through other physics experiments that I won't get into, that's when he earned his Nobel Prize, because his treatment was correct. So it's all math, right? It's all people making math. And this is the birth of quantum physics. And this is why you get these weird conclusions in quantum physics, because the math suggests that things are in two places at once. The math suggests that the particle doesn't know which door it went through until we observe it. The math suggests all these different things. Is it actually true? That's debatable. But that's the idea. That's why you see all these weird out there, quantum physics means consciousness type stuff, because according to statistical mechanics, that is theoretically correct. And the statistical mechanics is the best tool we have to analyze the universe right now. All right, so let's get into curriculum stuff. Rutherford and Bohr's contribution to atomic theory. This is stuff you actually have to know. So I'm going to pause and fix the current topic and stuff, and I'll be back in a sec. Okay, so I fixed stuff up. This brings us to Rutherford and Bohr. This is actual curriculum stuff. If we go back to, what you're supposed to know down here, explain how Bohr and Rutherford contributed to the planetary model of the hydrogen atom. So this stuff is actually important for the test. Everything here is actually important because theoretical background. I can't really talk about Bohr without taking you through what the heck this means. All right, so let's talk about it. So Rutherford and Bohr. The electron So the first thing, Thomson discovers the electron in 1897 by running electricity through atoms, and out comes this beam. He actually runs it through a vacuum, and then out comes this beam off of the cathode, and you could move the beam with magnets and with electric fields, and he found out that the beam was made out of negatively charged particles, which he called electrons. Very quickly, people started turning electricity, putting electricity to work to make chemistry happen. We have an entire unit about that called electrochemistry at the end of this course. But the upshot is now they realize that the atom is no longer indivisible, that electrons can leave the atom if you give them enough energy. You have to give them energy to make them leave. That inspired two different models. There's the plum pudding model that you guys know from Thomson. You might not know this one. This is the Nagaoka model, the Saturnian model. Nagaoka was a Japanese scientist, and he thought, this doesn't really make sense because negatives shouldn't be able to, hang out so close together, or positives shouldn't be able to hang out so close together. He proposed that there were negatives around the outside and a small dense positive center in 1904. And yet Rutherford gets the credit. Rutherford proved the Nagaoka model correct in 1911 using the results of the gold foil experiment. The gold foil experiment was actually done by his students. One of his students was actually Geiger, the same guy that made the Geiger counter. And the other one was a guy named Ernest Marstead, who was just an undergrad at the time. So his students did the work, and Rutherford mathed it out. He did the math to prove that his students' results could only be true if there was a dense positive charge in the center of the atom and a bunch of empty space, and then the electrons on the outside. So there's the Rutherford model of the atom. And at the time, they didn't even know that neutrons were a thing. Neutrons were only discovered in the 30s. So to explain the extra mass, he actually thought that there were protons and electrons in the center, and that was where the extra mass came from. He supported this with like radioactive decay and stuff. There's a whole story there. Interestingly, Rutherford actually knew about the Nagaoka model, and he said, "Hey, my results actually confirm this Nagaoka model much better than the Thomson model." It's right there in his paper if you want to read it. I'll link that down under the YouTube video. But Rutherford had this other student whose name was Niels Bohr, and Niels Bohr went to Rutherford and said, "Hey, I know my electromagnetics, I know my electrodynamics, and when you accelerate a charge, it loses energy. It has to lose energy because it's pushing against other charges, and so it has to radiate away energy. And if you're saying that the electrons are on the outside and they're going around and around and around, they should lose energy the whole way, and then they'll spiral into the nucleus and kind of explode." So Bohr very, very quickly put together his model, and Bohr's model was based on this stuff, right? This stuff, specifically Rydberg's thing, with the wave number. So the Bohr model posited that there's specific energy levels, and those were the N's in the Rydberg model. Those N's were actual specific energy levels, and those energy levels kind of roughly corresponded to how many waves can fit around the nucleus, how many waves can fit in a shape around the nucleus. And more waves took more energy because the frequency had to be higher based on Planck, right? Planck's energy quanta. So what Bohr did was he took Planck's idea of energy quanta and Rydberg's formula for spectral lines, put them together, and out came an even nicer equation that perfectly described different energy states of different atoms. And so Bohr ended up getting a Nobel Prize for this. Rutherford also got a Nobel Prize, but his Nobel Prize was about radioactive decay rather than any kind of atomic theory. But Bohr did end up getting the prize for that. So here we see that spectrometer that was Bohr's thing, and Bohr was able to make it fit the data for a lot of different atoms. So that's Bohr. You have to understand the concept of Rutherford and Bohr. One thing about this is this idea of waves in their orbits and only orbit where a specific number of waves fit around the atom. That was wrong, absolutely 100% wrong, but it worked. The math worked. So kind of like Planck, where he had to make this assumption, and then the math worked. Bohr got close to the truth mathematically, but wasn't quite all the way there. So we've talked about the curriculum stuff. We're going to finish with Schroedinger, which I've also misspelled his name. Wow. Let me fix that. There's an R missing. Schroedinger. There we go. Fix that R. We are going to talk about DeBroglie and Schroedinger right after I pause, and I'll be back. Okay, and I'm back. And the last piece here is electron waves, the electron cloud model of orbits, of orbitals. So basically, Bohr made this incorrect assumption that they travel in waves. Schroedinger and DeBroglie, actually DeBroglie first, DeBroglie took this concept of wave-particle duality that was discovered in experiments in 1923. That was when Einstein was proven right that light can act as a particle. If light could act as both a particle and a wave depending on the scenario, DeBroglie said, maybe if light can do it, if light can be a particle and a wave, because they thought it was a wave and it turns out it can act as a particle, he thought, why can't electrons, which are particles, act as waves sometimes? If we've already got evidence of light going from one to the other, why not electrons going from the other to the one? And he took that concept of, instead of the electrons moving in waves, the electrons actually being waves. He created this equation that fit in very nicely with the spectroscopic data that they were getting at the time. He got a Nobel Prize for it, blah, 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 for electron duality. And then Schroedinger, of Schrodinger's cat fame, used more statistical mechanics because the mathematicians had been developing statistical mechanics. And he created this formula. This is called the Schroedinger equation. It is one of the most important equations in history because it gives the 3D shape of what is called a waveform. And a waveform is a cloud of possible positions, essentially, for a particle. So using the Schroedinger equation, we get this cloud of where the electron can possibly be around the nucleus. We call this an orbital. An orbital is this cloud of probability, which I'm just really bad at spelling today. Orbital, probability. Orbital probability. There we go. Probability, and we call that an orbital. So electrons exist in these orbitals, what we call an orbital. So they're not round orbits like Rutherford thought. They're not wavy type orbits like Bohr thought. They do have specific energy levels, and each specific energy level gives it a specific orbital. And each specific orbital has a specific shape. So, this is a lower energy than this because it's a weirder shape kind of thing. But this is the same shape, just turned on its side. So these two will actually have the same energy. Same with this one and this one, they'll have the same energy kind of thing. Right? And then you have like circular ones, you have like kind of dumbbell shaped ones, you have like figure eights, you have multiple different ones. But all of this comes from this equation, this probabilistic 3D kind of vector equation that Schroedinger came up to explain deeper divisions in spectroscopy and other sciences at the time. But it all came through spectroscopy. And then the last piece, let's talk about the cat, because everybody likes talking about the cat. Schrodinger was a realist. He didn't like this concept of probability so much, even though his equation was so uh, dependent on probability. He didn't like this concept of there's a chance of this stuff happening. He thought, like Planck thought, that it was really an artifact of the math, and that you couldn't apply it to large objects. That's what the cat experiment's all about. He said we're going to have this radiation detector, and radiation is a quantum phenomenon because it's probabilistic. There's a chance that the thing is going to decay, and there's quantum mechanics that explains this is how fast it should decay because these are the energy levels, and this is what the protons are doing and the neutrons are doing. And he said we're going to hook that up to a detector. That detector is going to kill a cat if the thing decays. And then he said, according to my model, according to the interpretation of quantum physics, there's this superposition of states, and only when we look at it do we see the true state of nature. And this is dumb for cats because that would suggest the cat is both alive and dead at the same time. So Schrodinger's cat is actually a counterproof to say it's dumb to apply these quantum physics concepts to larger objects. And then people use it, of course, as like, hey, look, the cat's alive and dead at the same time. Isn't that weird? Which is exactly the opposite of what Schrodinger intended with his quantum physics, with his Schrodinger's cat thought experiment. This was a time when thought experiments were big. Physicists would get together in big conferences and just throw thought experiments at each other's theories, being like, but if you did this, then your theory doesn't work. And then the physicists would be forced to kind of improve their theory because of it. So that's Schrodinger's cat, that's orbitals. So we are very interested in this electron cloud stuff because that's what we're going to get into starting on Monday. What these orbitals mean, what it means for energy levels, and stuff like that. So last piece here is we're going to review. So I'm going to pause, write review, and we'll finish off the video. Okay, so finally, the last thing we're going to do is concept review. Keep in mind is now that emission spectra and energy levels, I really can't spell today, guys. Energy levels provide most of the proof for this model, and then the concept review is what we're doing. So, just briefly going over these notes. We started with talking about what the heck is spectroscopy in the first place. What is an emission spectrum? Different elements have different emission spectrums that match their absorption spectrums. You can use this, for example, to figure out what elements are in the sun. It's very cool. We talked about the hydrogen spectrum and how people started using math to explain where the lines are, starting with Balmer, who developed the theory of the visible lines, Rydberg, who expanded it to all of the lines, and then finally Planck and Bohr, who were able to expand this theory and actually talk about it being a physical aspect of the atom instead of just a way to explain what the lines were. Max Planck, of course, using spectroscopy and the blackbody radiation to develop this concept of light having specific energy levels, using more math to figure it out. Einstein saying that Planck's math was actually a real thing rather than an artifact. And using the photoelectric effect to prove it. And that's where we get the idea of photons, that photons can be treated, that light can be treated as a particle when we're talking about small amounts of light that are hitting a surface, or an atom, for example. Then we had Rutherford and Bohr that you guys have to specifically talk about, where Rutherford used the gold foil experiment that his students did to prove that there was empty space in the atom and that there's a concentrated positive charge in the center, because if it was any other way, then it wouldn't explain the backscatter of the alpha particles to the degrees that his students saw. So he proved it with math. It was actually just kind of fancy trigonometry. And then Bohr improved on Rutherford's model because things can't orbit forever. They have to lose energy. So he said, there must be specific allowable energy levels for the electrons to be in, and then they can't fall further because there's no energy level there. They're not going to slowly decay because there's They have to jump. And the jumps, he said, are what give these lines. Right, you see those jumps in this diagram here. Yeah, so that was Bohr's concept. So Bohr brought it all together using spectroscopy and this empty space idea and all the other stuff. So very important to explain how spectroscopy helped Bohr. And then DeBroglie and Schroedinger, who said they're not just acting as waves, they are waves, and so you have this probability distribution of where we can find the electron at any given time in the atom. The nucleus is in the center in these kinds of diagrams, so very, 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 very far to the center. Yeah, and then briefly we talked about Schrodinger's cat, but that's not really part of the curriculum. So that's that. I'm going to go back to this model thing here. Once again, you can find this model down below in the description. We found some of these, but what I wanted to show was the prediction. So here's what the billiard ball, this is Dalton's model, the very first thing where it's just a ball. It should just bounce off all light. Right? It should just bounce all light off. This is not what we see. We see emission spectra. We see this kind of stuff. The plum pudding model, because there's only, one specific energy level for the electron, it should all stack up in one place. All stack up in one place. This is not what we see. We see multiple lines for every element. The solar system model just goes kaboom because Rutherford didn't account for the loss of energy. Then Bohr went, there's specific allowable energy levels. That's what Bohr said, right? You see this electron jumping energy levels, and every time it jumps back, it releases an electron. See, when it jumps back, that's when the electron gets released, or when the photon gets released. When the electron jumps up, when it absorbs energy, when it jumps down, it releases a photon of different colors. Okay, there's the emitted photons gathering up there. This explains the spectrum perfectly. So that's why the Bohr-Rutherford model is often the one that we keep. We went a bit further. DeBroglie said that there are waves. These waves, you see these little waves. One wave, like 5 waves, 3 waves, 2 waves. So the energy levels are based on the number of waves that can fit. Right, and it's, it looks like this. There's different waveforms. That's DeBroglie's concept. And we can also go to a brightness view where we can see that similar kind of thing. So that's the DeBroglie vision, where the electron is no longer a single particle, right? The electron is no longer a single particle. It's actually a wave around the nucleus. And then Schroedinger came up with the equation of a 3D probability cloud rather than a single wave. So here's the 3D probability cloud. And you see that it suddenly changes shape probabilistically on which way it goes based on how much energy it absorbs. And that's what we're going to stick to. We're going to stick to electron clouds, and each one is an orbital, and each different shape has a different energy level. So you see it changing shape. So if you want to have a look at these yourself, look in the description. It's the PHET simulation. Feel free to read Rutherford's paper. It's actually quite a legible paper as far as physics papers go. Yeah, that's long enough for a video. I'll see you guys in class tomorrow. Thanks a lot for listening.